And okay, please open the file that, well, the same Excel file that we have been using for the last two sessions. We are going to use it this morning and tomorrow, I guess. Yes. So open that Excel file. Well, you should have it with you. You were supposed to be following me last week with all the estimations and all the things. Okay. And let me share my screen. So, well, just these are the things that we have been discussing these last days. Just basic. Well, a quick review. We have been discussing multiple decrement models, but essentially, what we are going to see this morning is that multiple decrement models are just a special case of multiple state models, and those are the models that we actually use the most in actuarial sciences. But these are the things that we have been doing. And we work on these, we estimate these probabilities, and I believe this was the last example from last session. Okay, yes. So remember, just and again, I know not all of you were in the actuarial mathematics last semester, or well, some of you were in that class more than, well, probably 2 years ago. Yes. So just remember, like, don't worry about this notation. This was just an example of how we can take this multiple decrement perspective and use it to estimate values for insurance, values for pensions, and for specific benefits that go beyond just the basic alive death model. Okay. And yes, so this is a topic that we didn't discuss last week, but I think I started giving you like a general well, an overview of this topic. So this is going more into like demographic topics, but because this is not widely used in actuarial sciences, but more in demography, because since we are essentially the people who are working with the statistics related to mortality, and we are the ones who know how to handle these things. We usually call demographers and essentially actuaries with background in demography, or demographers with background in actuarial sciences, to discuss the impact of specific causes of death. So we already know how to estimate certain probabilities. We can actually even estimate insurance benefits. But sometimes more from a policy perspective, or in order to inform or to identify specific areas of opportunity or areas of concern in public health or some other fields, we want to study specific causes of death. So we have two options. And the first one is what we call the associated single decrement tables. And essentially these tables, what we are going to do is we're just going to pay attention to one cause of death. Essentially, let's assume that there are no deaths in Mexico other than those who are created or the result of circulatory diseases. So we can create a life table for those specific causes of death. Of course, life expectancy will change because we are only going to pay attention to these specific causes of death. And it's more than just removing those deaths, and we're going to see how to estimate those right now. But what I think is the most common perspective, or the one that sometimes it makes more sense. I will dare to say that. Sorry, ignore my emails, please. But essentially, is what happens if we remove this specific cause of death. So again, it's not that we're going to pay attention to that cause of death, but we are going to remove that cause of death of our population and essentially follow the impact of mortality of all other decrements different from this specific cause. When we do that, we are working in what we call the cost deleted table. Essentially, we can remove, and let's think about like cancer and see, okay, so what would the value of life expectancy be if people were not dying of cancer in Mexico? So we can remove that cost. Or we could go to the associated single decrement table and say, okay, what would be a life table assuming that only cancer is in our population, which are probably a complementary, well, it's not opposite perspective, but sometimes it makes more sense just to remove these, because we can then tell people, okay, because you are not, and again, cancer is not a good example, let's say obesity, because you are not following healthy diet, you are not working out, or you are not trying to eat healthy food or whatever. Uh, this is taking away, on average, this many years of life expectancy, which is something that we can use. And again, it's not only like telling people you should eat healthy; it's also telling the government, okay, you should be paying attention to prices in food and access to healthy food and all these things. So again, it works in several ways. So what we are going to do is we have to adjust probabilities, because as I was saying, sometimes people just remove that cause of death from our deaths that we have from INEGI, and they just estimate the life table without those. And yes, that is a valid approach sometimes, but there are some adjustments that need to be made. And sometimes, I don't know, I never, well, not recently, I haven't done the well, the exercise of like checking the values that we get from both of these things. But essentially, the thing is, we need to adjust our probabilities, because even if we remove this cause of death from the deaths that we get from INEGI, the survival probabilities are still taking into account that that cause was around there. So even though we remove those deaths, the impact is being indirect in survival or some other aspects. So we need to fix or to change those probabilities. Here we call it the pure probabilities with quotation marks, because again, it's not that they are pure, there are still some issues going on. But it's the best approach that we have to work with these things. So the way that we do it is we're just going to take our probabilities from the life table, from what we call the master life table, the one that we have, and that's the reason I am telling you, please have your Excel spreadsheet open, the one that we used last week. So we're going to take these probabilities and adjust or estimate the new probabilities for this specific cause just by taking our probabilities to the power of this ratio or this proportion. And this proportion is essentially is that it's just the causes of death, or the number of deaths that we have for a specific cause, divided by the total deaths that we have in our population for each age group. So why is this the best approach? We're not going to work on the development of this new probability, but it's similar to the assumption that we had for fractional ages. If you remember from actuarial sciences, it's similar to this thing. Well, remember that in that scenario, we have something like this. Okay, so it's similar to this, how this is developed, but it's not for fractional age. It's for like the proportion of something. So it's like a fractional number of deaths that we have in this. So again, if we have time, or if you want me, just you can email me, or probably I should send you an email with the pages from the book that you can go and look for this thing. Okay, so this is especially when we want to, wait a minute, is this the one from your section, or is from the other section? Yes, this is from here. Let me just double check that I didn't. Okay, yeah, that's fine. So apparently we discussed this last week, but okay, so it's a good thing that we are going back. So when we work with cost delete decrement, essentially what we do is we remove one specific cost. So this ratio, the proportion that we are going to use, is going to be this value. We're going to express it with the negative I, essentially the negative cause of death I, again, like minus cancer, minus external causes, accidents, or whatever you want. And so we are going to estimate this value, Then we're going to adjust and get our probability using the expression that we had in the previous slide. And using the variables or the functions from our master table, or essentially the life table that we have from the regular one, we're going to estimate these new values, the probabilities, survivors, and these person years, well, not person years, the separation factor, which here I am missing this negative and this negative. Yes. And then essentially following the same formulas that we had, we can estimate person years lived between ages x and x plus n, person years lived between ages x and omega, and life expectancy after we remove one cause of death. So let's work with this. Let's start with this. So this is the life table that we have from, well, the two life tables. We have men and women for 2010 in Mexico. And this is the information that I gave you. Again, if you ever want to do this for your state, you will just have to go to INEGI and download the specific causes of death that you want. Okay, so but the process is the same. So let me just duplicate this table here. And delete this. We don't need this right now. Okay. So before I start, are you there? Do you have your Excel file open there with you? Let me know, please. Yes, and Sophia has it. Daryl. Okay, at least two of you ready. Okay, so I'm assuming most of you have it there, but you're just too shy to type. Okay, so let's choose one cause of death. So I don't know if you want to work with cancer, circulatory disease. This is the endogenous, essentially diabetes, or external causes, accidents, and murders, and all these things. So which one of these would you like to select as the cause deleted cause of death? Cancer. Okay. So let's estimate. Well, remember that this is neoplasms, just the general expression for all types of cancer. Okay. So let's estimate all deaths without this cause. So essentially, I'm just going to add this without including the value for cancer. Come on. I don't know, my computer has been doing this. So do it for men and for women. Okay. Now let's estimate the factor of the ratio that we are going to use. So just following this, since what we did was the thing that I have in the numerator, I'm just going to get this divided by the total number of deaths that I have somewhere here. Okay. And now we can estimate, well, we are going to estimate this probability, but we don't have P in our life table, but we have Q. That's fine. So let's just estimate. The value. We could do it in one step, like 1 minus and then to the power of this thing, but let's just keep the formulas as simple as we can. Why is it going all the way here? Men and for women. Okay. So now let's make this I'm just gonna take this formula and use this expression, which is to power this many decimals. Okay, are you there with me? Before I continue, because
No, poner la fórmula de RE.
Just the new total number of deaths without the first column divided by the total. And then, well, okay. And just because we are going to need it, let me just estimate from now Q, which is going to be, again, 1 minus this. And again, at the end, everybody has to die, so we still get the 1 for our last probability of death. A run out of coffee. So before estimating, wait, go back. Okay. Before going to estimate like the survivors, let's estimate the separation factor, because this is probably the most complicated formula out there, but again, and we needed to estimate the person years later. So remember that this is the length of our interval. We just got the Q's. We have the R. Remember, this is the negative R. I don't know why I didn't have it like that. And that's it. Okay. So let me copy these. Okay. So the length of our interval, I have it here. I have the variable here. And plus R times Q x, where is Q, divided by 1 times the separation factor, the original one, and the length of the interval that I have it variable here. Okay. And you should get values that are pretty close to the values that you originally had. So this is 0.089, 0.08970, 8972. So it's just a slight change. But again, we could not do this and just work with the other separation factors. But again, let's do things correct, like the proper way. So we don't have the last two. So we have for men and for women. Okay, so now we have all the information that we need. So let's start with our new survivors. LX. So essentially what we are going to do is we're just going to create a new life table. Well, not a new life table. We're just going to start new values for life table. Again, with 100,000. And in order to get the following thing, the following value, we use this formula right here. Essentially telling me, okay, those who are going to survive are those that you have times the probability of surviving or the new probability that you estimated. These times these new probabilities. again, it should be similar to the LX that we had before. Let me see. Mhm. Now, if you want, actually, no, if you want, we need these values. Those are dying, just the difference between the survivors. Now, person you sleep. So here's when, remember that this formula is the length of our interval, which is 1 in the beginning, but I always like to have this variable because it helps with the formulas, times the survivors, and then we subtract and the new separation factor that we had times those who are dying. And for the last one, number of deaths, here I'm just going to use the specific death rate that we have, even though this is probably, we could get the specific death rate for this without this cost, but I'm just going to do it like that for practical reasons. Okay, come on. Men, women. I'm kind of going fast because I'm assuming that you are comfortable with the life tables. Okay. And let me know if you get there or if you have, or you got stuck in some of these things. Okay. So let's just wait for another person who confirm that you're there. Okay, wonderful. So while the rest of you get here, the important thing about this cost deleted table is the following. Let me hide these columns. So essentially we can compare like how many years you have. Okay, separation factor is these values. Remember, didn't we call it like that before? remember that when we use these correction factors, yes, we use the Cohen-Devinay, one formula that we saw before. Remember that these separation factors, essentially what they are doing is splitting the total number of deaths that we have on those who belong to a different cohort. Essentially, over here. Remember that when we have our Lexis diagram, okay. So we also have we always have the number of deaths of people dying here, but we have some people dying here that these were born in this cohort, in this, let's say, in the year 2000, and these were born in 1999. Okay, so we could have something like that. So the separation factor, what is doing is taking all the deaths that you have in your population, and it's telling you what proportion actually belong to the previous cohort. So that is something important, because when the regular formulas or some general formula that we have for this, here the assumption was that out of all deaths that you have in 1 year in your table or anywhere, half of those deaths actually belong to the previous cohort and half of those belong to your cohort. So this is something that has to do with like person years live and how many years you are assuming that they actually spend in your population. And this half of those deaths actually, or they live half of the period, essentially makes sense for ages that are really like not really young and not really old. For instance, if you see here, you get 2.49, 2.49, 2.49, 2.49, essentially 2.5, which is almost 5 divided by 2, right? So it's really close. However, for the first years, here half should be 2, and this half should be 0.5. But this is not happening. And the reason this is not happening is because, remember, when people are really young, mortality here, close to this, the moment of birth, is really high. So essentially, when you have 1 year and you're saying, okay, how many people I have died or that died here, most of them are going to belong to my cohort from that year, and few of them are going to be for the previous one. So that reason this goes way below 0.5. And the next thing is also for and this is true also for the next group. So essentially, is doing this. It's just giving us a correction, and look, by doing this. So sorry, I updated this. What is this? It's a voice thing. I have a laser tag. Woohoo! Sorry, I updated this. So I don't know how to. Yes, it's still here. Okay. So that's the reason. This is the general formula, and we could use this for most years of age, but essentially the general expression for this is still, yes, the length of the interval for those survivors, but then we are gonna do this. So this is the separation factors. Instead of using is just half, is just, yes, the total of the interval subtracting this number of people. Okay. So I don't know if that's kind of clear, Fanny. Yes. Okay. So going back here. So even though we would expect probably, or for us, we would expect a higher impact on these things, it's still significant. Let me write the difference. So for men, okay, this is taken on average 1.6 years of life expectancy. So it probably doesn't look that big, But again, remember this is life expectancy, and this is only like taking into account only these types of deaths or these deaths because of these specific cause. Weird things happen here because again, really all ages, like some weird things can happen. But essentially, what is telling us is okay throughout the life course of this cohort. Remember, this is a fictional cohort, and we're assuming everything is going to remain constant, whatever. Cancer is taking out of our population, on average, well, out of the male population, 1.6 years of life expectancy at birth, essentially, um, well, 1.6 years, and for women, 1.8 years. So again, probably you tell me like 1.8 years is we already have more than 1 year on pandemic, so something that we can deal with. But again, this is significant because again, we have so many causes of death. We have people dying from different causes. So let's see what is the most significant one. We have the chart here at the beginning. I think it was heart disease. Yeah, well, it's really hard to see, but yes, circulatory diseases is significant. Here, all the other causes, again, we don't have, it doesn't make sense to go with the other causes, probably for men. Okay. Sorry, this is kind of more, it's weird the way that it's moving. Okay. So it doesn't matter, but again, we could have an, we can change the cause of death that we selected here for like for this example. No, I want to show it. So okay, what if we just instead of using cancer, we just exclude circulatory disease. So again, it's really easy just because we have it in general here. And here the difference is 3.6 years for men. So yes, because we know heart disease is the leading cause of death or deaths associated with heart disease. And for women, it's taking 3.8 years of life expectancy. And again, it's not that we are going to get rid of heart disease because it's not. Because essentially we are not. It comes with just the transition of the general transition that we are going through in Mexico. It's like we are expected to see more of these things. But let's say, what about external causes? And that is something that we could do here. So it's gonna be. This is for men, women. And for women, is external causes are taking half a year of life expectancy, which again is not big. But for men, it's taking 2.8 years of life expectancy. And yes, we know because we remember those charts when we saw cause of death. This is a lot, and most of these, essentially after age, I don't know what age is this, 40 goes down to one. But again, for women, it's like nothing going on here. This is negative. So probably what would be the meaning of this is like without taking into account external causes, women at this age will be reducing life expectancy. So probably this is has to do with again. We will have to pay attention to this, but essentially what we pay more attention is the first again because this is the accumulated impact throughout all life. Okay. So again, we could go into specific causes. Let me just I'm just gonna leave it the way it was from the beginning. Mm-hmm. We can go into specific causes of that, like here, these other causes. So what are these other causes? Probably we could open this group and pay attention to specific causes, or probably group together these violent crime, accidents, and accidents because of alcohol abuse, or like what other? suicide. That's something that people are studying in specific areas. Is not really in some areas is not a big problem, but for instance, some states like Tabasco has the highest rate of suicide in Mexico. So people are studying that, like why is in this state, what is happening in this state, uh, why people are killing more in Tabasco themselves, more in Tabasco than in other states. So and there are some people actually going and studying now because of all the oil and everything is spilling mercury. Is mercury? Or that's the country. Well, the element into the water, and that has an effect on your brain. A lot of things. So people are trying to study this, but again, we could uh, analyze these things, or probably if we go and let's say that we get hired by the population division of the United Nations, but not the global division in New York City, but we get hired by the African branch of the United Nations, which is in Ethiopia. We could be doing a lot of work with these things, probably grouping together all the infectious disease, like because people got like cholera, or people died of not cleaning water, or all these causes, and we can say, okay, all these preventable diseases that you have are taking this many years of life expectancy from your population, which makes sense, something that we could, and then we can go and talk to the government or talk to, I don't know, Bill and Melinda Gates Foundation and ask them for money to build, I don't know, a plant like to treat water. Again, so these are things that we do all the time. And here's where actuaries with that go into demography actually work a lot. We do a lot of work on these things, like trying to decompose life expectancies. And there are some techniques that we can actually use to identify more specific impacts. But this is a really easy way to tell people, okay, if let's say here we don't have, we didn't do it for diabetes, but diabetes was 2 years more or less. That's a policy that when we go out, we went out and told the government, okay, this is happening. So they started actually in the TV, they were, okay, diabetes is taking on average 2 years of life expectancy out of the Mexican population, which is something that was done by following this perspective. And again, we can go to specific states, we can go to, I don't know. We could create life tables, and it's really complicated in Mexico. But we could create life tables for income levels, and we can adjust for some other activities or characteristic that again we can have more specific information. So questions on this? We good? Okay. And sorry, I really love life tables. I don't know. This has been my life for the last 18 years, so I really like life tables. Okay. So if I get kind of really excited about these things because I like this topic. So let's move or let's go back to a more general perspective. And again, here I know Markov is there, but don't worry, we're just gonna use the easiest and the more general approach to these things um, for this for our class. And this is more going or trying to again linking together what the things that we know from demography and the things that we can do in actuarial mathematics. And again, for those of you who haven't taken that class, don't worry. But actually, a couple of you, or more than a couple of you, we spent like 2 weeks talking about these models in actuarial mathematics too, when that still existed. So multiple decrements models are just specific models in this general context of multiple state models. And multiple state models are used a lot of insurance because we can create or we can study how people are moving between different states. And of course, sometimes they can move back and forward, for instance, between being healthy and being sick. So people who are healthy can get sick and then they can go back to being healthy and stuff. It's really complicated to move from state to, at least in this model, because people who die are going to stay in that state forever. But let's see if we can generalize this. And actually, for tomorrow, I have to go back to my files, and I have a really nice example working with R, getting these things. I just need to remember how to do it. Well, I have it there. like I was trying to study transition between being employed with access to Social Security, being employed without access to Social Security, and being out of employment throughout life. So we can actually move between these things. Like think about it's more common, like for example, for men between moving between having access to Social Security and not having access to Social Security, at least between ages 25 to 60 something. But women, they have more transition. They can be working with or without access to Social Security, and then women are more likely to leave the workforce because demands of at home or because maternity and these things. And that is something that we can study following this perspective. Okay, so it is really complicated, and this is something important. Yes, the continuous perspective is really nice, but it's really complicated to work continuous perspective in these multiple states. And the reason for this is the following. Mhm. Last session, I remember that we defined the probability moving between state I and state I, essentially not leaving that state, similar to the probability of surviving from actuarial mathematics. Mhm. So all these options, okay? Let's J. Mhm. Essentially, with what I told you is okay. It's the same. When we were in actual mathematics, what the probability of surviving was the exponential, and then we get the integral between 0 and t of the force of mortality. Here is the integral between 0 and t, the force of transition. Again, if you pay attention to each state, essentially for healthy, I will add this force of transition from being healthy to being sick, and here I will add this one from being healthy to die. For this, I would add this one, and for that, the probability of staying in that state is 1. So I don't need to do any estimations in that. So that is fine when we only have one option, like one-way transitions, like in the multiple decrement perspective. And that's the reason I told you multiple decrements are specific scenarios for this, because there we have one state and you have all the possible transitions out of that state, but there is no way back. So people who died out of cancer cannot go back to being alive. People who died of heart disease cannot go back to be alive. But also important is that you cannot move between these states. Again, you die from one of these causes. There are no movements between these states. However, in this scenario, we have to be careful because we have two options. Mhm. Let's add this line, and this is probably a person that never leaves. Essentially, this person is in this state and doesn't move for any reason, this state. So this person is starting at age X in state I and is after at age X plus T is still at this state. That's fine. But we can have a more general perspective without the line in this, which is okay, the probability of a person who's starting at state I at age X being at that same state at age X plus T, but we don't know what happened in the middle. So one option that we have is that yes, this person actually never uh, never left. Hmm. So that's fine. And we have some other option, and this is a function like OH, just any function, where this is the probability of leaving and going back. So essentially, this person can be moving all this time, but what we want is the probability of this person leaving and then being here uh, by the time X plus T or by the time T, which essentially this is just giving us this. Hmm. So this one is really easy. We know how to get it. This second part is really complicated to get because, again, since we are in a continuous perspective, that will be the probability of a person who's healthy getting sick, and let's even think about getting sick in a more like serious way, not just getting a flu, like getting like a cancer or having I don't know, having going through heart surgery and all these things. Some people can go back to being healthy, but for instance, diabetes, once you get it, it's like you can control it, but again, you won't get rid of diabetes. Probably for insurance companies, if you have it under control, they can consider you being healthy again. But probably they don't. Again, this varies between insurance companies and the policies that they have in, well, the information in the policy, the general conditions, those are called. But again, it's really complicated to measure these things. So sometimes we say, okay, let's assume this is zero. So let's assume that there are not all these movements between states, or that there's no way that you can leave and coming back. Or let's assume that this is one half of the previous function. Or some people, for some specific diseases, they have it really, really well studied. Like now, okay, for instance, COVID. Again, I don't like using COVID because I think we're being bombarded well, so yeah, bombarded. We're having all this information regarding COVID these days. But essentially, we know the probability of getting sick. Yeah, that we know it. At least we have some general information. Then from being sick, we also have probabilities of death because we have enough information. Sadly, we have, in statistical terms, we have enough information to know the probability of somebody dying. But we also know the probability of this person, again, by definition or by contrast, we have the probability of somebody recovering from COVID. And we also have the probability of this person staying sick. Let's say that we're doing this by day. We know how many days this person will be with this disease on average. So we can model these things in different ways. But this is for COVID, which is something really important right now that we have been following, we have been studying, and hopefully in 5 years we won't be doing these things for COVID anymore. So we don't know. This is repeated, sorry. So what we usually do is, instead of going with this continuous perspective, which is again something that we could do, we can go in discrete time, okay? And we are going to measure transitions per unit of time. Again, these units can be years, can be months, weeks. It's up to us, and sometimes it's not up to us, it's up to the information that we have. But we are just going to work on that discrete perspective, okay? Which is something that you are way better than me at doing, because for you this is totally fresh. For me, this is 17, 16 years ago. So again, I always go back to these things. So here, and this is, I think one of you asked me when the first time that I opened this spreadsheet, like, why are you using Markov? Again, it's not that we are using crazy Markov things. We just have information on these transitions. These transitions are called, of course, Markov multiple state models, because we can track transitions per unit of time, and this comes in for a matrix, and we're going to see that probably tomorrow, actually. But we can have probabilities for these models. And this model, or the model that we have here, we have these probabilities. Well, essentially, we have these probabilities for that model. Okay. So we have from 0 to 0, essentially, people staying healthy, people getting sick, people dying, people who are healthy dying, and then people who are sick going back to being healthy, people staying sick, and then people dying, people who are sick dying. I don't have the other options. The other options that the options that I don't have are these. The reason I don't have it is because since state 2 is, I think, sorry, I think that you use the same expression for this. State 2 is an absorbent state, meaning that once you get there, you cannot leave it, okay? And I think you use the same expression in your stochastic models class, okay? So essentially, that means that transition from 2 to 0 are 0, from 2 to 1 are 0, and these are 1s. Again, this is something that we have, okay? Now with this, we can actually try to answer these questions. And again, these are, compared to the things that you have to do for your stochastic class things, these are really easy. So if we want to estimate the probability that somebody who's healthy at age 50 is healthy at age 52, what we can just track these movements, okay, like following this person. So we have the probability of a person who's age 50 being healthy, and then 51 being healthy. But we also have another option, right? We have this person who's healthy at age 50 getting sick and then recovering from that. Okay. So now we have this path instead of just one probability. Okay, so let's just estimate that. So just one. Okay, so one is healthy, no, 0 is healthy, 1 is sick, and 2 is dead. Okay. So this was this times this plus somebody who's healthy and sick times somebody who's sick going back to be healthy. Okay. Okay. This is 0.9608. And for B, the probability, now we want the probability of somebody who's healthy at age 50 being sick at age 52. Again, we have to see this as these transitions. Okay, so somebody who's healthy has to be sick. So this person can get sick at age 50, and then at age 50, this person has to remain in this state, or this person can be healthy and then having the transition, sorry, this is 51, at age 51. Okay, I think that's it, right? Yes. Okay, this is from 0 to 1 times 1 to 1 plus 0, 0 times 0, 1, right? Yes. And again, these are things that are really easy. If we have the information, if we have these probabilities, we can just work, we can just follow in these paths, okay? So we can have, for instance, and this is something that we are going to explore more in detail tomorrow, we can create for age 50 a transition matrix, okay? Where we have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 2, 2, 0, 2, 1, and 2, 2. Okay? So we can have our matrix. And let's just write the values for this. Okay. So 0 to 0 is 0.98. It's going to round to 12. 0 to 1, 0.012. Okay. And 0.068. Okay. And the following one, 0 to 1, is I'm really bad at rounding. I think it was 18. Okay, that's fine. 6. So we have this matrix for age 50, and then we have another one for age 51, and then another one for age 52. So again, sometimes it's better to have these things on form of a table, and sometimes it's better to have these things in form of a matrix, which is something that you probably have been doing. And yes, this is a really small matrix, but again, it's the same general idea. Okay, so going back to this example, or let's see if probably let's think about this, and I think it's better for you to try it at home. Again, you don't have to do it because I know not everybody has taken this class or the extra mathematics, but we can use these transitions to estimate things like this example. Okay, we have somebody who's age 50, a healthy life. This is important. Who's buying a policy, is purchasing a policy from our insurance company, and most insurance companies actually will have the requirement of you being healthy in order to buy insurance with sense. And this person is going to be paying premiums of 10,000 annually at the beginning of every year, up for 5 years. Okay, so that's the period that this person is going to be paying premiums. The insurance company decides or includes a benefit in the policy stating that if the policyholder gets sick, and again, this getting sick is something serious, not just getting a flu, this person will not pay premiums during those years, which is really nice. And of course, once marketing department, because these things usually come from sales or marketing, whatever, they come out with this idea, then they ask actuaries in the company, okay, estimate the impact of this benefit. Essentially, let's estimate the reduction of the expected present value of the premium income, essentially the income that we might receive from premiums from the waiver. Essentially, let's estimate the expected present value with and without the benefits, and see how essentially we include this perspective into the actuarial field. Okay, and assuming an interest rate of 4%, we can actually do these things. So we don't have we have the probabilities from the previous example. We have an interest rate of 4%. My invitation is try to do this. Again, don't spend too much time in this because I know you have a lot of things to do for some other classes. But for those of you who already had the actual mathematics class, which is most of you, just try to do it. And tomorrow we can start with this example. Let's estimate this example and see how essentially we can move between these states. Okay? Agree? Or no? Okay. Yes, and tomorrow we're gonna go back to this matrix perspective again. Here we have I have the room to do these things, and let's go back to discuss this matrix perspective. But I think it's better for us to go to check that tomorrow. I'm gonna dig into my files and try to find that example from a real data set that I have. I'm gonna try to clean that data set, because again, if I give you the raw data set, it's gonna be like, what's going on in here? So let's do that tomorrow, right? So if any questions on this? No? Well, if there are no questions, let's leave it here for this morning. Again, I think I'm gonna try to leave like these sessions shorter because I know we are tired, and yes, it's been a lot of time in front of the screen. Okay, so if there are no questions, see you tomorrow. We are gonna finish tomorrow with these multiple state models. Remember that next week we won't have class because again, Labor Day and Congreso. And then we still have 3 more sessions, and those sessions we're going to discuss survival models, but I think more with hands-on data, working with R, which I think is really useful. Okay, so see you tomorrow. Bye. Bye, nos vemos.